So to continue our work in understanding nonlinear systems and equilibria of nonlinear systems, I want to talk about generic and non-generic equilibrium points. So generic equilibrium point, that's things like saddles, spiral sources, and spiral sinks and nodal sinks. Those are called generic equilibrium points. Non-generic equilibrium points, okay, those are going to be centers and repeated roots. And we have a theorem that says the linearization about a generic equilibrium point will match the behavior of the nonlinear system near that point, but that linearizations are inconclusive for non-generic equilibrium points. So what does that mean? That means that when we came back to our previous example, which I'm bringing up, and we linearized the system, and we saw for the linearized system that 0, 0 was a source, then that's true for the nonlinear system. When we saw that 2, 0 and 0, 3 were sinks, that was true for the nonlinear system. And when we saw that 1, 1 was a saddle, that was true for the nonlinear system. So I can go back to this picture, and when I labeled these points as sinks and saddles and sources, that was the correct thing to do for the nonlinear system, because the linearization is telling us what's going on for the nonlinear system. Okay? So those are generic and non-generic equilibrium points. And for the generic ones, the linearization will match the behavior of the nonlinear system. As for stability, we can look at a system, we'll call it y prime equals f of y, and an equilibrium point y0. And we can let j be the Jacobian of the right-hand side f at y0. And if the real part of every eigenvalue of j is negative, then y0 is asymptotically stable. And if the real part of at least one eigenvalue of j is positive, then we say that y0 is unstable. So you can go back to our example, and I'll kind of roll back to our example, and we'll see here, okay, that 0, 0 is a source, and that is unstable because both our eigenvalues are positive. 2, 0 is a sink, that is stable. Actually, that's asymptotically stable. Okay. 0, 3 is also a sink, that is asymptotically stable because both eigenvalues are negative. And 1, 1 is a saddle, that is unstable because one of the two eigenvalues is positive. So that's how we use the Jacobian and the linearization to talk about the stability of the equilibrium of a nonlinear system. I want to go back to one more example, and that was the predator-prey system. So we looked at this predator-prey system. We were looking at rabbits and foxes. R stood for rabbits. F was for foxes. Okay? And we looked at the behavior of this system. And if you remember, we found two possible equilibrium values. Okay? Those equilibrium solutions were 0, 0. Okay, that's the boring one where nothing happens. And 10/9, 5/3. Okay, those were the two equilibria for the system. So what we can do is we can find the Jacobian of this system. Okay, we can take the derivative of the first equation with respect to r, and then we'll get 2 minus 1.2 f, and then take the derivative of the first equation with respect to f, so we get negative 1.2 r. And then we can take the derivative of the second equation with respect to r, so that we get 0.9f. And then take the derivative of the second equation with respect to f, which gives us negative 1 plus 0.9r. And that's the Jacobian of the system. Okay, so if you remember, okay, if we plug in the equilibrium points, so the Jacobian at 0, 0 is going to be 2, 0, 0, negative 1. Okay. So that tells us 0, 0 is a saddle and unstable because one of the eigenvalues is positive, one's negative. So lambda is equal to 2 and minus 1 for that diagonal matrix. Okay. But that's kind of a boring solution anyway. That's where we have no rabbits, no foxes. Okay, what about the other equilibrium? Okay, so that's 10 ninths and 5/3. We want to plug that into our Jacobian matrix. So 2 minus 1.2 times 5/3 minus 1.2 times 10 ninths. We're going to get 0.9 times 5/3. And finally, minus 1 plus 0.9 times 10 ninths. Well, what do we get when we run that? We're going to get the matrix 0, minus 4/3, 3/2, and 0, actually. Okay. If we want to find the eigenvalues, the characteristic polynomial, hopefully you can see that it'll easily that it's lambda squared plus 2, and that equals 0. Oh, so lambda squared is equal to minus 2, and lambda is equal to plus or minus I times the square root of 2. Oh. So the second equilibrium point, it says that says that the linearization is actually a center. Well, what we can say is the real part of the eigenvalue is 0. Okay, so it's not negative. Okay, the linearization is a center, but we cannot conclude that for nonlinear systems, that the nonlinear equilibrium is a center. Okay, so we get to this point, looks like a center, but the theory does not allow us to immediately conclude that the nonlinear equilibrium is a center. Okay, but did this give us some sort of hint as to what's going on? Okay, and the answer is yes, it did. So I'm going to flip over to slopes, and I'm going to bring up the phase plane, and this is the predator-prey system, and you'll notice when I put in some solutions that it certainly looks like that equilibrium point is actually a center. Okay, it actually does. But what's fun is so the theory can't conclude that it's a center, but it certainly ends up looking like a center. 0, 0 though is actually a saddle, so you can see that near the equilibrium there, that 0, 0 does look like a saddle. So we can use this theory to give us some sort of insights into the nonlinear system.